Hello and welcome to our capstone project, developing an anisotropic muscle tissue phantom, sponsored by Dr. Mark Pacey of the Penn State Biomedical Engineering Department. In BME450W, B samples are used as a low-cost biological surrogate for muscle tissue, allowing students to study real tissue mechanics in a laboratory setting. However, Dr. Pacey must prepare by hand, a process that takes many hours and yields inconsistent samples. In addition to being labor-intensive, the beef samples slip out of the tensile tester, require PPE to handle, and have a short shelf life. To replace the current system, the new phantom needed to be easy to prepare, consistent, shelf-stable, and mechanically anisotropic, while remaining compatible with the Lloyd tensile testing machine. Our team addressed these requirements through a three-step process: analytical modeling, materials testing, and mold design. An initial literature review revealed that there were no predicate devices. Through further research, we determined that embedding fibers within a matrix was the most effective approach to achieve anisotropy. Using the rule of mixtures, we then developed an analytical model to estimate the fiber volume fraction required to achieve anisotropic behavior and identify feasible composites for physical testing. Next, we conducted materials testing on select fibers in a silicone matrix. We also tested several composites to assess how the fibers interfaced with the matrix and sample compatibility with the Lloyd machine. After several rounds of material testing, it was confirmed that the silicone was compatible with the Lloyd machine. The red cotton monofilament and green cotton multifilament successfully demonstrated anisotropy after the surface was mechanically roughened by running scissors along the thread. 3 iterations of the mold were developed, with the final design consisting of 4 layers: an acrylic base, 2 sheets of laser-cut acrylic, and a neoprene gasket layer to prevent leakage. The mold also includes 33 fixation points, allowing screws to uniformly compress the layers and further reduce seepage. A statistical analysis comparing the intrinsic and extrinsic properties of the samples confirmed that the mold produces uniform specimens, and the total preparation time for 150 samples was reduced to just over 1 hour. Through iterative design, modeling, and materials testing, we developed a tissue phantom capable of addressing the limitations of current biological samples used in BME450W. While this work is primarily designed and simulation-based, it establishes a reproducible framework for consistent anisotropic sample fabrication. Future work will focus on experimental validation and direct comparison with biological tissue under tensile loading conditions.